And then there's a gap, and that would be in the center of O2n, and there we have the center characterized.
Ah. Right at the center of SO2n.
The problem is that this element, the one you propose and the inner candidate,
Doesn't
the
lie.
product is not in SO2n.
Yes.
So we really must get to
Well, of course, you could argue as follows, I guess. So it's certain. You're right. The other component is. What's the other component generated by? Anything of determinant -1. And you picked an element of determinant -1, you conjugate with that. So it commutes with it. So maybe that implies and lies in the center of O2n.
fix an element of determinant -1, we would be done. Because we know it acts trivially on the ones that have determinant 1, so the whole co-class would be fixed element by element. But we don't know if it chose an element of determinant -1 goes to another and to another.
Well, so okay, let's see. So we chose an element, say, sigma in O2n minus SO2n. Say any element. So then we said if there is an A in SO2n, so that sigma is adjoint of A. So then we said that sigma inverse A adjoint is the identity. Doesn't that mean it lies in the center of O2n? The kernel of the adjoint is the center, right? Does the group have to be connected for that? That the kernel of the adjoint is the center? Yes, the adjoint is a derivative of something, but that has to be connected. Yeah, it's a small problem. Do you have a different solution? No. I had a different one, but I thought this one was easier. Okay, let me tell you my solution. So let's take a specific one. So let's say A be the matrix, which is minus 1, 1, 1. So diagonal minus 1, 1, 1, 1. And then let sigma be a conjugation with that matrix, restricted to SO2n. And I claim that's not inner. I can argue as follows. So let sigma be adjoint of, say, let's call it capital A. A lies in SO2n. then I look at the fixed point set. What is SO2n sigma? So that's the matrices that commute with this A, right? So what does that look like? We need to commute with this particular matrix. Block forms, right? So 0, 0, I don't know, xy, whatever. And that xy is equal to 1. And now can argue as follows. So it's, if you want to, it's, say, isomorphic to O to n minus 1. Because I can look at it as a following set of matrices of the form A, 0, 0, det A, and A lies in O to n minus 1. Right, so whatever here, I can justify to make the whole determinant equal to 1. So these set of matrices, because this is 1 by 1, right? These set of matrices are the same thing as this, and that to identify with the O, with the element in A, so that's isomorphic to O to n minus 1. So the fixed point set is O to n minus 1, and now I can look at the rank of the groups. So my argument was going to go by the rank of the groups. So what's the rank? So dimension of the maximum torus, right? What's the rank of SO2n? Remember that? It was diagonal matrices, rotation matrices, right? They had a 2 by 2 block. So here I can fit in n 2 by 2 blocks. So the rank of this 3D group is equal to n. And what's the rank of the fixed point set? Or the identical points, the same thing. So now when I have 2 by 2 blocks, I can't put anything to the last one. So torus is 1 less. Rank is n minus 1. But I claim that can't be because if I take this was conjugation with an element A here, right? So A is an element in SO2n. That means that there exists a maximal torus T contained in SO2n, which is an n-dimensional, right, such that A lies in T2n, in Tn. Right? So that means it commutes with that. So that means that SO2n sigma, right, sigma was assumed to be adjoint of A, conjugation by A, contains an n torus. So the rank must also be equal to n. So the rank of the fixed point set is equal to n minus 1. But we just saw for this particular element A here, it's equal to n minus 1. So that was going to be my proof. But I wonder if I can fix this. Yeah, I think several of you guys gave me that proof. I looked at it, oh yeah, that sounds nice, but you're right. So for those who came late, this was a problem where you're supposed to show that SO2n has an outer automorphism. And there's a problem that this doesn't necessarily right away imply that this lies in the center of ON. Right? So the conclusion was supposed to be that sigma inverse A is an element of the center of ON, or O2n, which is plus or minus identity. And that would then imply that sigma is plus or minus A. Right? That was the end of the proof. It's only since the adjoint identity for connected Lie groups that implies it's in the center. Right? But this element here does not lie in the identical component of the orthogonal group. By construction, it lies in the other component, in fact. So this conclusion here, you're applying to a group which is not connected, and then it's not true anymore. So the general theorem was that if G is connected, then the kernel of the adjoint is the center of G. This was a general result we discussed. But if G is not connected, that may not be true anymore. I see. You're right. Proof was not correct. Subtract another 5 points from your exam. Okay. Thanks. Any other questions? I was going to bring you some problems that we should discuss on, that I'd like to discuss on Friday, but my laptop broke down, so I couldn't do it this morning. I have another one at home, so I'll do it at home and post and send it to you tonight. So probably, I don't know, 5 or 7 problems, something like this, which you can take a look at and present it on Friday. Something on symmetric spaces. It could be good to do some exercise on symmetric spaces. Okay, so let me finish the explicit examples I started last time. So you can recall 2 facts. I had a Lie group G. Sigma was an automorphism of G. G was connected. It's a square entity. And K was a subgroup which is contained in the fixed point set, but contains the identity component. Plus K compact. That implies that G mod K is a symmetric space. And the other fact was that if I now have a subgroup L inside G, which is preserved by this involutive automorphism, this implies that L divided by L intersected K inside G divided by K is totally geodesic and symmetric. So there's some nice natural totally submanifolds inside the symmetric spaces, which I can get from the involution. Okay. So I forget if I finished I think I only started the Lagrangian subspaces. Probably didn't finish them, so let me make some more comments. So M was a set of Lagrangian subspaces. And here we could say, do this for the canonical symplectic vector space. So omega naught of, say, here identified R2n with Rn plus Rn. And omega naught of xy was inner product jxy, where jx is minus yx, standard complex structure on R2n. And then I can just define the symplectic form in this fashion with respect to the standard. Again, the standard inner product R2n if you want to. So the same way that the complex structure in general is related to a Kähler forms. This now for this, just in this canonical situation. And then M was defined as a set of subspace in R2n. Dim L is equal to n, and omega restricted to L is equal to 0. So these were symplectic subspaces. And we had another interpretation, subspaces in R2n, such that J of L, J naught of L, is perpendicular to L. There's another interpretation in terms of which is interesting in terms of representation theory. The part I didn't discuss. So this also equal to the set of maps tau from R2n to R2n with the property that tau composed with J naught equals minus J naught composed with tau. And tau is an isometry. And tau squared identity. So such taus are called the real structure. So this means complex antilinear if you want to. They're not complex linear, they're complex antilinear. They're isometries and they're involutions. And these are important representation theory. So I'm not going to discuss this relationship, but if you know the representation theory, this might be interesting for you to understand. It's in the notes. Okay. then we already discussed that certainly SPNR acts transitively on this set of Lagrangian subspaces, but there is no metric on M such that SPNR acts by isometries. So if one computes a stabilizer, which I didn't do, but that was an exercise, the stabilizer is incompact. So there cannot be any metric invariant under the natural group, which is a symplectic group acting on this thing. But there's a smaller group that acts transitively also. So, but UN contained in SPNR acts transitively. That's the claim. And it's compact, so now there will be an invariant metric. So for this, remember what UN was in relationship to SPNR. It was those isometries that are symplectic. So this was one of these things we discussed in the very beginning. Isometries are symplectic. Isometries of R2n to R2n. So here, SPNR acts on R2n, right? So isometries here, which are symplectic, they are unitary. It's a nice kind of relationship. So I already know that this acts transitively. So all I have to convince myself is that the element that takes one to the other, I can also make it orthogonal. That's all I'd have to know. So how did we say that θ is transitive? We took a standard symplectic Lagrangian subspace, which was a span of the first n vectors, so equal to Rn plus 0 in that decomposition. Right? That's certainly symplectic with respect to the standard symplectic form. And if L was any symplectic subspace in M, then we claim there exists an orthonormal basis. Forget what we call it, U1 up to UN, V1 up to Vn, such that omega naught has a standard form. And UIVJ is delta ij. So I think we may have argued this already last time. So how does it work? Take one vector, make it a unit vector, right? Certainly can do that. Then, so a vector in L. Then take J naught times the vector. Is that how it went? How do we construct this basis again? Step by step somehow, right? So I start with U1 in L, certainly. Then I want to choose the V1. Then I choose the V1 in L perp, such that omega U1 V1 is equal to 1. It's non-degenerate. It vanishes on everything in L. There must be something in the rest with which this omega is non-zero. I can certainly make it line L perp. And now I know that omega restricted to the span of these two vectors is non-degenerate. And I keep on going. Right, so, but the nice thing is that in this construction here, I can choose this basis to be orthonormal. And now I just argue that if, say, A is the basis change from this new basis U1, UN, V1, Vn to the standard basis, then A of L is equal to L naught. Okay. And of course, this is now unitary, so L lies in is an isometry because these are both orthonormal bases, so L lies in O2n. But it also lies is symplectic, again by construction, and that was UN. Okay, so I have a much smaller group that acts transitively. And that often happens that, so you have some natural geometry you want to look at, the group is quite large, but there's something natural that's smaller. For example, on the sphere, I can look at the conformal group, right? Things that don't preserve the inner product but multiply by the constant. That's a non-compact Lie group. And there's no metric on the sphere invariant under the conformal group. They don't exist for the same kind of reason as stabilizer is not compact. But of course, inside the conformal group, there are isometries, and they're transitive, and that has a metric. So often one can make the structure group smaller and get something invariant. You can always do that because I think at some point we discussed this theorem that if I have a Lie group, there's always a maximum compact subgroup. In fact, the Lie group itself was then a product of the maximum compact times the Euclidean space. Once I have a maximum compact subgroup, that might act transitively, and usually does. Anyway, so now I have the transitive action by a compact group. All I have to compute the stabilizer to see what the space looks like. So what's the stabilizer? So now I take an element A in UN. Say let's take the stabilizer of M at the point L naught. Right? L naught is my base point. So I want to look at those matrices where A of L naught is equal to L naught. A lies in UN, intersected S, and of course also then in S of 2n. So it's orthogonal. So A also takes L perp to L perp. So A breaks up in the block form. And the question is, what are those blocks? So I claim it should break up into block form where this is a B and this is a B, and B lies in O2n. That's my claim. So block form is clear. The additional claim I make is that these two off-diagonal matrices are equal to each other. Let's see, why is that?
Because it is complex linear.
Ah, yes. So now we have to remind ourselves what this embedding looks like, absolutely. So embedding of UN in SO2n was of the form, I take a matrix, break it up to a real imaginary part, and then it gets sent into the block form A, B, minus BA. Minus signs may be here, I always forget. So, but anyway, to be complex linear, these have to be the same. Okay. So that means now that I have my stabilizer, so the whole manifold. M is UN mod ON. Well, now ON sits inside UN in the natural form, right? That A goes to A. It's the same matrix. It's real, but now can consider it complex linear. Now to see it's a symmetric space, I have to construct an automorphism, but this is a fixed point set. So, but I claim it's clear what it should be. I want the things in sigma that fix something to be ON. So it's a real matrix inside the complex matrices. So it's conjugation, right? So it's a symmetric space. There's some additional comments one has to make. So it's UN mod ON. because this group here is not connected, that means the space can't be simply connected. Right? So if I take un mod SON, that should be a 2-fold cover. So this here is my M. I will call this M naught, which is oriented Lagrangian subspaces. So just we have fixed orientation on the subspace L. And so another exercise is, which we should discuss on Friday, that pi 1 of this oriented Lagrangian subspaces is equal to Z. Turns out it's actually the same thing as unoriented. Oriented is the same thing. It's also equal to Z. And the fact that it's equal to Z is important. So this gives rise to something that I may have mentioned at some point. That's called the Maslov index in symplectic geometry. Namely, if, say, alpha is a closed path of Lagrangian subspaces, then it can associate with an integer called the Maslov index of that path. And that's a symplectic invariant of path of Lagrangian subspaces. Very important in symplectic geometry. So this fact is very useful. Inside Lagrangian subspaces, either version, well, inside un mod on, I have also sun mod on mod son. So un has a center, has a one-dimensional center. I can look at the subspace that has determinant 1. And I notice that if A lies in SUN, then sigma of A also lies in SUN. Right, that A bar is that A bar is that A bar, and that's 1 again. So it's a subgroup. SUN inside UN is a subgroup invariant on evolution. That means that this is also a symmetric space. And totally geodesic inside all Lagrangian subspaces. By this previous result that I mentioned, fixed point set of evolutions are symmetric and totally geodesic. One can ask the question, well, so there I have the subspace. What does it mean geometric in terms of what additional thing do I have to acquire of the Lagrangian subspaces to lie in this totally geodesic submanifold? So, I have to look up again. I think there's there's something called special Lagrangian subspaces. So this is my set of all oriented Lagrangian subspaces. This here is, I call it MS. MS are called special Lagrangian. And if I remember right, I should look that up maybe, they are the ones that preserve a complex volume form. Right, this is determinant 1 inside UN. If it preserves some kind of volume form, that would imply determinant 1. But now it has to be a complex 1. Have you seen that before? Who does symplectic geometry here? Was you, right? You do symplectic geometry, right? Have you heard about the special Lagrangian subspace before? And in what sense do they preserve a complex volume form? Look it up for next time. You should know that. it's important in symplectic geometry, these kind of special Lagrangian subspaces. They have been used a lot in symplectic geometry over the last couple of years, last 10 years or so. So look it up and tell us on Wednesday. Okay, so that's maybe enough about. Maybe the last comment is that SUN mod SON is an irreducible symmetric space. But UN mod SON is not. So this is isometric to SUN cross SON cross a real line. It's compact, cross a circle. This is true up to covers. And then I can see isometric here. So in other words, there's a natural map from here to here, which is an n-fold cover. Kind of, remember we had this discussion that there was a map, say, from SUN cross a circle onto UN, which is an n-fold cover. And you convince yourself that if I divide by SON, I also get an n-fold cover again. And then it's actually an isometric product. But they're actually diffeomorphic. So, but UN mod SON is diffeomorphic to the product. But not isometric. It's diffeomorphic, not isometric. Kind of the analysis discussion we had about Lie groups, that the relation between UN and SUN cross a circle was also that they're actually diffeomorphic, but not isomorphic, but didn't respect the group structure. But this was an n-fold cover of this one as far as the group structure is concerned. So isomorphic and diffeomorphic is a little bit different. Same here, isometric and diffeomorphic also a little bit different. For a similar kind of reason. Okay. Of course, then maybe the other exercise, where is it here, that fits into this here, that if I then split off that factor, that should be simply connected. So a set of special Lagrangian subspaces form a simply connected totally-geometric submanifold inside all Lagrangian subspaces. Okay. One more example before I go on to general theory again. I'm not going to cover all of the ones in the notes, but I think the following one is very useful, namely the set of inner products on a vector space. So Euclidean Poisson vector space is a symmetric space. So let's quickly discuss this one. This is a prototype of a symmetric space that's not compact. All the previous examples were compact. Here's something what something looks like that's not compact. So let's say do this again for Rn. I have a canonical inner product in Rn, the usual one, usual orthonormal basis. And then I look at some other inner product. On Rn, and I can write that the way we already did this sometimes in terms of a matrix A. So that's my fixed inner product, and this is described by A. Right. And then, since this is symmetric here, this will be the same thing as XAY. But if I switch these two here, that means that A is symmetric, so A is a symmetric matrix. And I also have to have that this inner product here is positive, so the x, x must be positive, and that means it's positive definite. So another way of describing that space is a set of symmetric positive definite matrices. So now M is a set of A in GLNR. A is symmetric, and A is positive. Okay. So now we just look at this space in terms of matrices, a little bit easier to study. And then we have a transitive action there. I claim that GLNR acts on M by conjugation. So let's take a matrix B in here, an element A in here, which is again a matrix. Then B acting on A is BA B inverse. Notice that's again symmetric. It lies in M again. Right? For conjugated symmetric matrix, I get another symmetric matrix. Sorry, that's not true. I need a transpose here. Right, now if I take the transpose, I get B, A transpose, B transpose, A transpose A, so it's a symmetric again. Right? So it's like a basis change. And if A is positive definite, then this is also positive definite. So that's an action on M. I claim it acts transitively. I claim that's obvious. How do I do that? So pick an inner product, or pick a matrix A, then what?
Pick a vector.
Yes?
I want to take it to the diagonal form 1, 1, 1, 1, 1. So I normalize that vector, and then I take the complement with respect to the product given by A. A must split in a block form, and the lower square is non-shared.
Okay, that's one way to view it. Maybe a more geometric way to view it, where I don't have to take any normal form. If I have two inner products, then there exists an A in GLNR that takes an orthonormal basis to an orthonormal basis. Right. Each inner product has an orthonormal basis. Choose one. The inner product, of course, is determined by the orthonormal basis. If you have two of them, I just look at the basis change. It goes from one to the other, and this action here is basis change. So it's maybe the same thing, but a bit more geometric. So that's transitive. What's the stabilizer? So I have my natural inner product inside M. What does that get identified with? In this space right here. Well, so if I look at, this is how I described, went from inner product to matrix. So if this is the zero matrix again, the standard one, then A has to be identity. Right, so this corresponds to A equals identity inside this description of M over here in terms of matrices. So the stabilizer identity, where's the action? So it's the one, so A goes to B, A, B transpose, and that should be equal to A again. That's what it means to be stabilizer. So what does that mean? Oh, A's identity, right? Ah, okay. Stick the identity to identity, right? But this is how it acts on a general matrix A. I want it to be a stabilizer, but a stabilizer is a special point, which was my inner product identity. So that's those matrices B, where B times B transpose identity. So B lies in the isotropy of GL and R at the identity. if it's equal to ON, if it's orthogonal. So now describe it as a homogeneous space. So I can describe in two ways, either as matrices or as inner products. Sometimes one is more convenient than the other. For this here, I want to describe it as inner products. So I have two inner products, my standard one and my new one. Each one has an orthonormal basis. Once I tell you what an orthonormal basis, so to describe an inner product is equivalent to saying what an orthonormal basis is. Right? So choose one here and choose one here, arbitrarily. Now there's an element in GL and R which takes one from the other, like a basis change. And that's what this does. This is like a basis change, or the matrix A, which describes my inner product. Okay. So you're going back and forth between inner product and matrix. So in this case, that's convenient because it's more geometric. That's often the case. If you have two descriptions, that's usually very useful because you can go back and forth. One might be easier than the other one for certain things. So my inner products is now GL and R mod ON, sitting inside GL and R. Now, what about components? Is this connected or not? Because? Right. So this has two components, that plus 1 minus, but that positive, that negative. This has two components, that plus 1 minus 1. So each component cancels each other. So if I want to, in other words, I can write as GL plus NR divided by SON. So in each coset, there's one where this lies in GL plus NR. So it's connected as a space, a set of these inner products. Is it symmetric? So I have to describe the involution. That makes it into a symmetric space. So it should be an involution on all matrices whose fixed point set is SON. So I want the things that are fixed by it to be the defining equation of an orthogonal matrix. So that tells me what this should be.
B transpose.
Almost. Now it's symmetric, a fixed point set of symmetric matrices. And it's not an automorphism. Right? Taking a matrix to its transpose, that reverses the order, so it's not an automorphism. Inverse. That undoes again the switching the order. This now becomes an automorphism. And of course, the fixed point set. Are the matrices where B is B transpose, that's ON. Okay, so kind of what you want to achieve tells you what the automorphism should be. There's no choice. This has to be the automorphism. So that means N is symmetric now. Again, there's some special things one can say about it. Namely, this space is not irreducible. as a symmetric space. I can split off something again. Maybe I claim that first you have, of course, an SLNR inside GLNR. So I can look at SLNR mod SON. That's a subspace inside all the inner products. Because in terms of matrices, this would be the symmetric, positive, definite, determinant 1 matrices. Right? So that's what this is here. So it's kind of a normalization of the inner product if you want to. Now notice that sigma of SLNR lies in SLNR. Well, sigma here is sigma. If dat B is 1, then dat B of the transpose inverse is also equal to 1. So sigma preserves this, which means this is totally geodesic. And this is symmetric then. So the normalized inner products are also a symmetric space inside a set of all inner products. And I claim that one's irreducible. So that we're going to see shortly. We're on Wednesday. So claim is SLNR, what SON is irreducible. And the whole space is now a product again. And this time it's, I think, isometric. SLNR mod SON cross R now. What should that R factor represent? Pardon?
Like a volume.
What inner products should it represent?
The diagonal ones.
Diagonal ones, right? So in this set of matrices, it would be multiples identity. In terms of inner products, it's those which are a constant times a canonical one. That's
e to the lambda.
Yes, if you want to make it into a multiplicative group, then it's e to the lambda, I guess. Okay. So the question, is it an n-fold cover or is it an isometry? I think it's an isometry. Let me put a question mark here. We'll see that later on. And also we see that later on easily that this one's irreducible. Right now it's not so clear at all. This should be the case. And the last fact then is that makes it simply, well, they're both simply connected. Because here I take a product with a real line, not with a circle, unlike for the Lagrangian subspaces. And this, however, is the granddaddy of all non-compact symmetric spaces, in the sense that every other one sits inside this one as a totally geodesic submanifold. So we're going to be able to prove that later on. Take any non-compact symmetric space, and there's a very natural embedding into the symmetric space. So it's like the granddaddy of all of them. That's a nice fact. Okay, that's the examples I wanted to do. Let's go back to general theory. There's some more in the notes, but I don't want to spend too much time on it. Okay, first, let me make an important difference between what we call a symmetric space and what I want to call a symmetric pair. So let me define a symmetric pair. So a pair G, K, sigma is a symmetric pair. Well, if all these things are satisfied that we required, right? So I just want to formalize it into a name. Plus K compact. But I now want to also add the assumption almost effective. And remember, almost effective was the same thing as that G and K have no idea in common. So that was another way to think of something being almost effective. So I call that a symmetric pair. So in example, a word of caution. So remember, this certainly implies that G mod K is a symmetric space, by what we proved, but not conversely. So let me, in the following sense. So let's look at the round sphere. That's SON plus 1 mod SON. Of course, we know that SON plus 1 is the identical component of the isommetry group. And so this means that this is a symmetric pair, right? So and in this case, the symmetry sigma was the conjugation with the matrix, which is this matrix. The fixed point set was SON. So that's a symmetric pair, but now I can do the following to describe the same space in a different way. I look at the odd-dimensional sphere that sits inside R2n, which I can identify with Cn. And now inside SO2n, which acts on my sphere, I also have the UN, the complex linear one, acting on Cn. And of course, inside there I have SUN also. This here I should think of a sphere radius 1. And then at some point, I think we already discussed that SUN also acts transitively on the sphere with isotropy SUN minus 1, block form again, right? So I describe the sphere in a different way, or in two different ways, as SON plus 1 mod SON minus 1, but only for n odd. And then as a homogeneous space with respect to a smaller group. And so it's also SUN mod SUN minus 1. And the claim I want to make is that if I look at that pair, SUN minus 1, this is not a symmetric pair. Although the quotient is a symmetric space. But the quotient haven't changed the metric. It's still the round sphere metric. That's transitive. So I wrote it as a homogeneous space, or the Riemannian homogeneous space with respect to the round sphere metric. That acts by symmetry, that's a stabilizer. So you might think that this is a symmetric pair. The answer is no. So claim is there exists no involution. So exists no involution sigma such that the fixed point set is equal to SUN minus 1. What would be a good way to prove that? It's actually a good exercise. So you have to use some property of symmetry spaces that tells you that. Well, I could do it several ways. So maybe one observation just to get you started. I claim sigma can't be inner. If there exists such an automorphism, it can't be inner. Why is that? It's actually the same kind of argument discussed in the very beginning. if it's conjugation by a matrix, then the stabilizer contains a maximal torus. Therefore, they have to have the same rank, but this, I think, n and n minus 1. So such a sigma, if it exists, couldn't be inner. And that gives you an idea how to prove it. Or another way to prove it was we had another characterization of symmetric spaces that with respect to reductive complement, the Lie brackets in P lie in K. So another possibility is check that this is not true in this case here. So this can happen sometimes, that inside the symmetric pair, like the isometric, for example, inside the symmetric pair, there might be a subgroup ALK inside K such that G mod K is also L mod something. Okay, then it's still a symmetric space, Lx by isometries, but it's not a symmetric pair anymore, usually. Okay, so this is good to have this kind of terminology, symmetric pair. And often you leave the sigma away here. It's understood then there's a convolution in the background. Okay, so the first thing I want to discuss is curvature of a symmetric space. So here I do assume a symmetric pair. Again, whatever formula I'm going to write down would not be true if I describe it in terms of something like this. That formula I'm going to write down wouldn't hold here. So it's very important that we have a symmetric pair. And then we have our Cartan decomposition. Then remember with that we can identify P with a tangent space at, say, the identity coset of G mod K. And the way that went was that I took a Killing vector field in P and evaluated the Killing vector field at my base point, which is K here. That was our identification with the tangent space. And also remember that important property of the Cartan decomposition is that P comma P lies in K. But this here was plus and minus one eigenspace of D sigma. So minus minus is plus, so PP lies in K. That is really special. And as we saw, that's essentially characterization of a symmetric space on the level of the algebras. And now I claim, so then the following thing holds. So now I want to write down a formula. So then let me describe the connection first. Let's see. To do this in the right generality. For any vector field y on G mod K, and for x star with x in P, the following thing holds. Nabla x star y is equal to the Lie bracket between x star and y, evaluated at the point P naught. So let's call the identity coset P naught, just have a more convenient notation. So connection is just given by Lie brackets. Okay. In the application, we're going to see it's very useful to prove this for y be any vector field, although typically we're going to apply it for something y utilizing P. Since P describes a tangent space, to describe the connection, all I have to know is what is nabla x star, y star, when x and y lies in P. That is sufficient to describe it. Also know, so, because this is at P naught, right, so here. If I tell you what the connection at P naught looks like, I know what it looks like everywhere, because G acts by isometries and is transitive, so that describes the connection, given my Lie brackets. B, if I want to describe the curvature, then I take three vectors in P. I want to describe what's the curvature applied to x star, y star, z star, but again, only at the point P naught. And that I claim is a triple Lie bracket. and I always forget the sign, minus. If you use a de Carme definition of curvature, it's a plus. So I like mine opposite to de Carme. So here, because this here is on the manifold, these are vector fields on the manifold, right? I apply the curvature to this. I take the vector field evaluated on the point P naught. This here is a Lie bracket inside the Lie group G. Right? This becomes again something inside the Lie group G, and then I take star of that and evaluate the point P naught. Notice here is another thing one can observe. X lies in P. That means a Lie bracket X and Y lies in K, from being a symmetric pair. Right? That means if I take the Lie bracket again, this is an element of P. Right? So K, comma P lies in P. So the other property of it being a reductive pair, that Kp lies in K. Plus one eigenspace, minus one eigenspace, minus one eigenspace. So indeed, this element right here, by definition, by being a symmetric space, is an element of P. Because now this equality here, again, should be then interpreted that, well, this is equality in the manifold. Okay. Now, at some point, we're often just going to use a short form that if x, y, and z lie in P, then nabla xy is Lie bracket, and r x, y, z is triple Lie bracket. With the understanding, what does that mean? It means I have to do it at my base point P naught. And x, y, and z lie in P, so identify that with a tangent space. It's our usual convention, and this holds true at the point P naught only. It doesn't hold true everywhere. Right? Only at the point P naught at the base point. But that's enough, since that determines the whole connection and the whole curvature. Curvatures at other points are the same. Okay, so let's do the proof. So part A here, I use a fact that X star is killing. That means the flow, let's call it phi sub t, by isometries. What else do I know? I skipped the description of what the geodesics look like in my symmetric space, and I actually need at this point. Okay, let me. So what will the idea be that I can describe Lie brackets in terms of the flow, right? To describe Lie bracket, you can take the flow of this vector field, pull this one back to a single point, and take the derivative. Right? That's one way to describe the Lie bracket. To describe the coherent derivative, I can describe it by pulling back with pair translation. Okay, so these are two ways of looking at the left and on the right. And here we will have to prove the claim. We have to prove the claim that the flow, so phi t, is equal to xtx, or in other words, if you want a left translation by xtx, right, acting on G mod k via left translations, right? So I claim that's the flow, and that's precisely the transvection is the transvection in the direction or for the geodesic exp tx times p naught. So this claim contains two pieces, which we're going to prove probably on Wednesday. First, that this is a geodesic. Right, so let's break this up into two parts. We're going to prove if x lies in P, then exp tx times P naught is a geodesic. So for that gamma t, then gamma of 0 is the base point, and gamma prime at 0 is x. Interpreted as an element in P, which identifies the tangent space. So this first claim is going to describe what all the geodesics look like in a symmetric space. And a very simple description. It's just take a one-parameter group in the direction of a vector of P and apply it to the base point. So it's very easy to compute geodesics in a symmetric space. And then the second part is that the transvection T sub T, which I remember was a symmetry around gamma at T over 2 composed of the symmetry at gamma 0 is xp. So these were two separate claims. And let me do those on Wednesday. If I have those, but let me just say if I have those, so using 1 and 2, I can see on the one hand what is this Cohen derivative. I can say it's d dt of parallel translation, but that's the derivative of the transvection back to my base point. At t equal to 0. That's because this part here was parallel translation. That was a basic property of transvections. And this is then also the Lie bracket between x star and y, because tt is the flow of x star. So then I'm just pulling back with the flow to a fixed point, the vector field y here. And that's one way to compute the Lie bracket. Okay. So that's the usefulness of transvections, right? It's a flow, and the flow is by parallel translations. That helps me compute the Cohen derivative, and it happens to be equal to the Lie bracket because of that property of transvections. So using 1 and 2, this A follows. But let me just see how A implies B. So of course the definition of the curvature. So I have to do a triple Cohen derivative. And this is my sign convention. So it's opposite to the Carmo, which is a sign convention in most books. Word of caution. So recall maybe, because we have simply discussed in the very beginning. If I take the Lie bracket between the action vector fields, or the Lie bracket in the Lie algebra, and then look at the action vector field corresponding to that, how they're related. Maybe I didn't discuss it. I claim there's a minus sign that one has to be careful about. So here is on the level of Lie algebra, here is on the level of the manifold. It's not quite the same. There's always a minus sign. And the reason is since flow of x star is left translation by xpx, and the flow of x as an element in G is right translation by xpx. So this here is something we discussed in the very beginning when we talked about the Lie algebra. And this here is, of course, is also a vector field on the group, and its flow was given by right translations. Whereas this here, how was the action field defined? I take a point, I let xpx act on it, and differentiate. And how does this act? This acts by a left translation on my homogeneous space, G mod K. So its flow is left translation, its flow is right translations. And remember that if I take if I were to define a Liebeck in two different ways, namely I could do it with left invariant vector fields or could do it with right invariant vector fields, take their Liebeck, and they differ by a sign. So that's something we discussed in the very beginning. So because of that, for the same kind of reason there, and because of this kind of dual role, I get a minus sign here also. Plays a role right here, right? Whether a minus sign or plus sign here depends on whether I take the bracket inside or outside. But here it doesn't play a role because I do it twice. Okay. The claims are still there. This was for a symmetric pair. So I have to see what do these these double co-derivatives look like by using part A. Now I have to be careful. So of course I want to use part A twice, I guess. So Y is any vector field here now. So my vector field Y is going to be this one here, to which I apply this equation here. So that is first Lie bracket in X star and nabla Y star Z star, and then evaluate the point P naught. Now you're very tempted to use A again. Right, I know how to compute this thing here. That's a Lie bracket again. But you're not allowed to do that. In fact, if you did this, notice that what you would get, so if this is again Lie bracket in Y and Z, Lie bracket in X, that's not this. That would be the other Lie brackets, right? So you can't do that. Why not? So if I were to say, so question mark, right, is this the same thing as X star, Y star, Z star? And if it has to be wrong because the form is different, right? So what's wrong about that? Well, so notice that I wrote this equation down at the point P naught. And it doesn't hold everywhere. It doesn't hold everywhere. And for this, I would have to do, if I want to take a Lie bracket with something here, I'd have to have an equation for this expression which holds everywhere. Or on a neighborhood of the point, at least, where I want to compute it, right? And this here are only equal at the point P naught, but not everywhere. So I can't do this. Okay. So I have to have a different trick. So for this, so this one was okay. So this here was okay. Now I use that the flow of X star let's call it phi t again. It's left translation, it doesn't matter. It's by isometries. So I can compute this object over here also in the following way. It's ddt, it's a Lie bracket. ddt of phi star t of nabla x, y star, z star. And then at t equals 0. Or dd phi of minus t if you want to put it back, right? So maybe a better way to write this is ddt of d phi minus t of nabla y star, z star. So that's just because it's by isometries, because it's a Lie bracket. And as isometries respect the connection, so I can say it's the same thing as nabla ddt of nabla, let's write like this again, phi star x star, phi star y star, and what is that? Or did I do the wrong? And it's a yz here, right? Y star, z star. So I want to differentiate this now with respect to t. So how do you differentiate this with respect to t? There's two arguments, right? It's bilinear, so you have to use a product rule. Right? So first differentiate this and evaluate t equal to 0, and then the other way around. So I can say it's nabla of ddt of phi t star y star. And now I get a z star because at t equal to 0, that's phi is identity, plus y star, and now ddt of phi t star of z star. So that's the product rule. Well, but now I can interpret this again as a Lie bracket, because it's a flow. So I can say, well, this is equal to nabla x star y star z star plus nabla x star y star z star. And now I claim that this is equal to the second expression. At the point P naught. And that's because I claim this expression right here is 0. This vector is 0. So why is that? Well, this is equal to minus, take the bracket first, then take star of that at the point P naught. But x and y lie in P, so this is an element in K. Which means that if evaluated at the point P naught, it's equal to 0, because K was a stabilizer. At K is precisely those things in G that fix the point P naught. So if the Lie bracket lies in K, anything at K applied to P naught just gives me identity, so it gives me 0. So this vector here is 0. And this cone derivative here only depends on the vector at this point, but not on the neighborhood. So this part is 0. This part is this part then. And now I can apply A. Right, now do the cone derivative only once. So x star, y star, z star. Because at the point P naught, again, only now at the point P naught only. Now, okay. I can apply this here once at the point P0. So now I'm almost done, and maybe I won't carry out the rest, but notice that what I did is I took a term like this, and I would complete in terms of brackets in the Lie algebra. So there's the same thing here, same thing here. Now everything's brackets, and then it boils down to the Jacobi identity to bring it to this form here. But the trick is to, say, translate these double cone derivatives in a clever way to something that only is in terms of Lie brackets. And that's what this does. Okay. We'll then derive various consequences of that, the fact that we know that what the curvature is. I want to say things about the section curvature, for example, and stuff like that. So we'll do that on Wednesday.